All right, so now that we've taken some time to learn how to solve exponential and log equations, we're going to apply this to some application problems. So primarily we're going to be looking at solving exponential equations and building exponential models in this video. So the first application we have for exponential functions is applied to finance and specifically periodic and continuous interest. So this is the idea of compound interest, which basically means if you take a sum of money and you invest it, not only are you earning interest on the initial investment, but you're earning interest on interest as well. So over time, compound interest just continues to build and build and build on itself, and it's a much better investment than just plain old simple interest where you're just building off of your initial investment. So we have two different types of compound interest. We have the periodic interest formula, which is basically where the interest is compounded a specific number of times each year, so maybe once a year, twice a year. And then we have the continuous interest where you are constantly compounding that interest. So if we look at some of the variables in here, in both of these equations, A is going to be the balance in the account after a given number of years, after T years. P is your principal, that's your starting balance, that's your starting investment. R is your interest rate, and we always make sure to write that as a decimal. So for example, 10% you would put in as 0.1, right? On this one, N is the number of times your interest is compounded each year, and T on both of these is going to be the time in years. And it has to be time in years for this formula to work. Okay, so let's take a look at an example and let's use some of these formulas. So our first example says we want to find the accumulated value of a $7,000 investment, which is invested for 9 years at an interest rate of 11%. All right, so we have a $7,000 investment, 9 years, and 11%. Okay, so first of all, if we take that information, our $7,000 investment is our principal. 9 years is our time. And 11%, if we change that to a decimal, is our rate. Okay, so then we want to do a couple different things with it. So first, it says we want to find the accumulated value if our interest is compounded annually. So compounded annually means that the interest is compounded one time at the end of the year, meaning n equals 1. All right, so if we take all this information and plug it into our formula, since we have a specific n value, we're going to use the periodic interest formula. We'll get A is equal to 7,000 times 1 plus 0.11 divided by 1 raised to the power of 1 times 9. All right, now when you plug this into your calculator, be careful to either make sure you use enough parentheses or plug it in steps. So if you want to just plug it in steps, what I would recommend is plug in the fraction 0.11 divided by 1 and then hit enter, and then plus 1, enter, raised to the power of, and in parentheses, 1 times 9, enter, and then times 7,000. So do it in a bunch of steps, right? If you want to plug it in all at once, make sure you add parentheses around this fraction and make sure you add parentheses around your exponent, right? And if you do, add all those parentheses in all the correct places, you should get the right answer. But just kind of play with it a little bit and see how you're more comfortable plugging these in, whether you like to be generous with your parentheses or whether you like to plug it in steps. So if you plug this in, you should eventually get 17,906 and 26 cents. All right, so our next one says we're compounding this now semi-annually. So semi-annually means compounding it 2 times every year. So everything else is the same, it's just that our n value has changed. So our a now is going to be 7,000 times 1 plus 0.11 divided by 2 raised to the power of 2 times 9. Again, if you want to plug this in all at once, just make sure you add your parentheses here, okay? Otherwise, you can do it in steps. And if you plug this in, you will get 18,350 and 26 cents. So you'll notice that as we increase the number of times that our interest is compounded, we increase the final amount that we're going to get, which makes sense. If you compound your interest more frequently, you're earning more interest, so you're earning more money overall. All right, next we have monthly. So this would mean it's being compounded 12 times every year. That would be 7,000 times 1 plus 0.11 divided by 12 raised to the power of 12 times 9. Again, make sure you add your parentheses if you're going to plug it in all at once. And we would get 18,753 and 87 cents. All right, so lastly, we have continuously. So when it says continuously, that simply means we're going to use our continuous interest formula instead of the periodic. So notice the continuous interest formula is using that natural exponential function with our base of e, which if you recall is on your calculator. So we're just going to plug this one in as 7,000 times e to the power of 0.11 times 9. And if we plug that in, we'll get 18,838 and 64 cents. So you can see that our trend continues here, that as the number of times compounded increases, your final amount that you get back out increases as well. So higher compounding, or more frequent compounding, I should say, is going to be a better investment for you. All right, let's take a look at this next example. So this time we want to know, how long will it take $25,000 to grow to $500,000 at 9% interest compounded continuously? So $25,000 growing to $500,000 at 9% interest compounded continuously. Okay, so we're starting with $25,000, so that is our principal. We want to end up with $500,000, so that's our accumulated value. 9% interest, so R is 0.09, and compounded continuously means we're using our formula A equals PE to the RT. All right, so plug everything in. So we'll have 500,000 is equal to 25,000 times e to the power of 0.09 t. All right, and we want to know how long is it going to take, so we're trying to solve for t. So this goes back to what we were doing in the previous section of solving exponential equations. So in order to solve this, we need to isolate our exponential term. So divide by 25,000 on both sides, which would give us 20 is equal to e to the power of 0.09 t. All right, from here then, we use the definition of a log to change this into log form. And since it's a base of e, it's going to change to a natural log. So natural log of 20 is equal to 0.09 t. Divide by 0.09 on both sides. and then just plug it in your calculator. So natural log of 20 divided by 0.09. If we plug that into our calculator, we get approximately 33.29 years. All right, let's do one more with these finance equations. So this time we want to know what interest rate is needed for $25,000 to double after 8 years if compounded continuously. Okay, so we're starting with $25,000. We want it to double in 8 years if compounded continuously. So we're starting with $25,000. Oops, starting with, so that's our P. All right, starting with $25,000, we want it to double, so our A is double that, so it would be $50,000. Our time is 8 years, and compounded continuously means we're using our continuous interest formula. All right, so plug everything in. That's going to give us $50,000 is equal to 25,000 times e to the power of r times 8. So we need to solve for r. So we want to isolate our exponential term. Which means we're going to divide by 25,000 on both sides. That'll give us 2 is equal to e to the power of 8r. Change into log form, which again we have a base of e, so that would be our natural log of 2 is equal to 8r. And then divide by 8 on both sides. So r is equal to the natural log of 2 divided by 8, which if we plug that in, gives us 0.866, which as a percentage would be 8.66%. All right, so that is it for our finance examples. Okay, so again, when we're looking at compound interest, we can use the periodic interest formula or the continuous interest formula based on the number of times that it's being compounded. All right, so in the next video, we're going to look at just more general exponential growth and decay as applied to things like population growth and bacteria cultures and things like that.